Having learnt that dl dt, although for a single particle, is equal to tau, now we enunciate the principle of the conservation of angular momentum, and that tells you if tau is 0, this means dl dt is 0 or L is a constant. You are already familiar with the use of this condition in the previous, maybe your lectures in 12th grade. Let me just show it to you. You are all familiar with Kepler's laws, and one of them is when the earth is moving around the sun, or any planet is moving around the sun, in equal time they cover equal areas, and this is nothing but a manifestation of the conservation of angular momentum. Let me show you how. You see, if I take this sun as the origin, the force is always directed towards the origin, and therefore tau, the torque r cross f, because r and f are parallel, is 0, and therefore the angular momentum must be conserved. Now you see, in this case the velocity at any given point, recall your planar polar coordinates, could be in r dot direction and perpendicular to this. So, velocity in general is r dot r plus r phi dot in phi direction, and therefore angular momentum is r cross v, v is r dot r plus r phi dot phi times m, which is equal to r cross r is 0, m r square phi dot in z direction. M is a given mass for a given particle, r and phi dot keep changing, z is a fixed vector. So, therefore, dl dt is equal to 0 implies that d over dt is of r square phi dot is equal to 0. And you can see that this r square phi dot is nothing but r square phi dot is equal to 0, r square phi dot therefore is a constant, and r square phi dot is nothing but rate 2 times the rate of area sweep. That is, given in r, this area you can see is roughly r square delta phi in time t divided by 2. This is r, this is r delta phi. So, the change of area in time delta t is r square delta phi divided by 2, divided by delta t, you get r square phi dot over 2 as the rate of change of area, and constancy of this implies constancy of rate of area sweep. So, the Kepler's second law, which says that the radius vector in a planet's motion sweeps equal areas in equal time, is nothing but a manifestation of the conservation of angular momentum. This becomes a powerful tool to solve problems involving angular momentum, as we will see in the examples as we go along. Having done all this for a single particle, I am now going to move to many particles, because after all, when we deal with a rigid body, it consists of many different point particles. So, now we are going to go to make ourselves familiar with angular momentum for a system. When I say system, that means many particles of particles. So, what we are going to consider is there are many different particles given, and by definition angular momentum is going to be the sum of angular momentum for each one of these particles, where I runs from 1 through n, 4, 5, 6, there may be n particles, 7, 8, 9, 10 and so on. So, this is nothing but summation m I, that is mass of the ith particle, m1, m2, m3, m4 r I cross V I. That is it. L total is nothing but summation over m I r I cross V I. We can use this definition now to relate the total angular momentum to the angular momentum of the center of mass and plus angular momentum about the center of mass. Recall from our previous lectures where I was talking about center of mass, and I kept on emphasizing the center of mass is a very important quantity, and we will use it again and again, and you will see again in rigid body dynamics it becomes a very central concept. So, let us now write L total, which is equal to summation I m I r I cross V I as summation I m I. Let me write r I as, suppose I will just make a two-dimensional plot. This is the center of mass of a distribution of particles. I will call center of mass coordinate RCM, and the coordinate of a point particle, ith point particle with respect to Cm as r I prime. So, this is r Cm, and with respect to this the point is given at r I prime, and this is r I. Similarly, the velocity would become v of Cm plus V I prime, where, let me write explicitly, r I prime is coordinate of point I with respect to the center of mass. V I prime is the velocity of point I with respect to the Cm. So, what we get is, given a distribution of particles L total is equal to summation I m I r Cm plus r I prime cross V Cm plus V I prime, which I can open up and write as summation I m I r Cm V Cm plus summation I m I r Cm cross V I prime plus summation I m I r I prime cross V Cm plus summation I m I r I prime cross V I prime. Look at this term, second term, RCM is common to all. So, this can be written as RCM cross summation I m I V I prime. Similarly, look at the third term, VCM is common. So, this can be written as summation m I r I prime cross VCM. A minute's thought will tell you this is the total momentum with respect to the center of mass, and that is always 0. Similarly, this is the coordinate of the center of mass with respect to the center of mass, that is also 0. So, these two terms drop out. What I am left with is, therefore, that L total is equal to summation I mi RCM cross VCM plus summation I mi Ri prime cross Vi prime. Again, this is a common quantity. So, this is only summation mi, which is the total mass RCM cross VCM, plus this is nothing but coordinate with respect to center of mass, velocity with respect to center of mass. Therefore, this becomes nothing but L about Cm, and this quantity is nothing but as if there is a massive particle of mass m moving with velocity Vcm at distance Rcm. So, this is nothing but the angular momentum of center of mass, and therefore, I can write L total as equal to L of Cm plus L about Cm. This is a general result. Irrespective of whether a body is rigid or not. So, you see we have not used the rigid body condition anywhere. The total angular momentum of the body is going to be a sum of the angular momentum of its center of mass plus angular momentum about the center of mass, equals L Cm plus L about Cm. And you can see if total momentum of a body is 0, that is m Vcm is 0, this implies L equals L about Cm, and therefore, in that case the angular momentum of the body, no matter where I take it from, is independent of the origin, because this has always come out to be L about Cm, but this is only because the total angular momentum, total momentum of the center of mass is 0. In general, this is the result. You can see this is also a result which depends on the property of the center of mass, that is summation mi Ri prime with respect to center of mass is 0, and similarly summation mi Vi prime is equal to 0. So, this decomposition cannot be done about any arbitrary point, that is I cannot say L equals L some point O prime plus L about that point O prime. It is only with the center of mass, because center of mass satisfies these two equalities, that I can decompose the angular momentum in this manner. This must be kept in mind. So, what we see is that L is equal to L Cm plus L about Cm. Let us take a simple example of it. Let us take a bicycle wheel rolling on the ground. If it is rolling, this point is not moving instantaneously, and therefore, if it is rolling with speed v and its radius is r, I have omega equals v over r. So, I can consider this motion as if the center of mass is translating with velocity v, on top of it this body, let me just say this is point A, point B, this whole thing is translating with velocity v, and on top of it with respect to center of mass, this is moving with omega equals v over r, so that instantaneously this point is at rest. So, the angular momentum for this, if I take the origin here, this is r, is going to be, this is r Cm, this is v Cm. So, you can see right away that L of center of mass is going to be m r v Cm, where r is the radius, r Cm cross v will give you only this projection, and L about Cm, this is going to be in the direction perpendicular, r cross v is going to be perpendicular going into the page. I am not worrying about the direction right now. L about Cm, since this is rotating like this, is also going to be m r v Cm. You can calculate that, and therefore, with respect to O, the angular momentum is going to be 2 m r v Cm. On the other hand, let this be the ground. If I shift my origin here, let us call it O prime, say by a distance r prime, then LCM is going to be equal to m r plus r prime VCM. However, L about CM is going to remain the same, and then if you sum the two, you get L about O prime. This fact that L about any point is equal to L CM plus L about CM also gives rise to something known as the parallel axis theorem in relation with the moment of inertia. I am sure you have heard of this theorem, but we will come back to it later when we do rigid body dynamics. Right now, we are trying to make ourselves familiar with angular momentum. How about the dynamics now? How about dl? I am dropping the suffix t right now. dl dt for a many body system. Let us work that out. Recall, when we are doing the momentum change for a many body system, we had this as d over dt summation mi ri dot, which had given us mi d 2 ri dt square, which was nothing but summation over f I, where f I, that is on ith particle, the force was nothing but the external force, that is something I apply externally, plus the force j not equal to I on ith particle due to other particles. And we had shown then, and that is how we came to center of mass motion, that this summation over I and j gives me 0. If f I j, the forces between the particles, satisfy Newton's third law, that is f I j is equal to minus f j I. The force on ith particle due to j is opposite and equal to force on jth particle due to I. A similar derivation now we are going to do for the angular momentum, and let us write this as d over dt of summation I mi ri cross vi, which gives me summation over I mi dri over dt cross vi, this being the velocity, this term cross product is 0, plus summation I mi ri cross dvi dt. Mi times this acceleration dvi dt is nothing but the force on the ith particle. So, this gives me summation I ri cross fi, where fi is the total force on the ith particle, that is the force including the external force plus the force due to other particles. So, dl dt for a many particle system, that is there are many particles which are interacting with each other, they may be interacting with each other and there are external forces applied on each one of them, is equal to summation I ri cross fi, which explicitly I will write as I ri cross fi external plus summation over j, that is all the other particles applying a force on the ith particle, j not equal to I, which I can now write as dl dt equals summation I ri cross fi external plus summation I j I not equal to j ri cross f I j. Recall, this term now I want to show to 0 in order to prove that dl dt equals ri fi external only. So, I can write summation I j I not equal to j ri cross f I j since I and j are being summed over, I can interchange them and write this as summation r j cross f j I. I have just interchanged j and I j, I not equal to j, and therefore, I can write this term summation I j, I not equal to j, r I cross f I j is equal to 1/2 of summation I j, I not equal to j, r I cross f I j plus r j cross f j I. And if f j I is equal to minus f I j, this term becomes equal to 1/2 summation I j, I not equal to j, r I minus r j cross f I j, and if f I j is parallel to r I minus r j, parallel or anti-parallel, then this term is 0. Fortunately, in mechanical problems, most of the forces are such that they are along the line joining the two particles, and therefore, this term always 0, and therefore, we get dl dt for a many particle system also is equal to tau external. This is going to be our dynamics equation. As I showed in the example of one particle, solving this gives me the resultant motion of the particles. Let me conclude this lecture by saying, by getting our main results. Number 1, six degrees of freedom to describe the freedom for rigid body motion. Three for translation, and 3 for orientation change. The tremendous reduction in the degrees of freedom comes because there is a constraint of two particles being at the same distance no matter what the motion is. Number 2, the dynamics is going to be described by dl dt. By dt equals tau external under certain conditions, that is, the forces are equal and opposite and along the line joining two particles, and this gives me the dynamics, and L for a system is equal to L Cm plus L about Cm, and fourth, if tau external therefore is 0, then L is a constant. That is the conservation of angular momentum. Having developed these ideas on angular momentum, in next lecture onwards we are going to apply them to describe the motion of a rigid body.